So that was a lot of theory. Here's an example. Going back to the data with the IBM return and the S&P 500 return. Here's a scatter plot. There are 30 points, each representing a month. And what you can see is that if the S&P 500 had a positive return for the month, then because the slope is positive, IBM also tended to have a positive return. Yeah, and likewise when it's negative. So, but the question is IBM more volatile than the S&P 500 index? So in other words, does IBM have higher returns when the index does well and lower returns when the index does badly? So that, in terms of the model, means is beta greater than 1? Not just 1, but greater than 1. Here is the corresponding R output of the regression. So we have here IBM return as a function of S&P 500 return. The intercept is implied. Here you have the estimate of the slope and the estimate of the intercept. And then you see some output here, well, standard error, that's convenient, and there's already some tests included here. And the tests included correspond to the hypothesis that beta 1 equals to 0 versus unequals to 0. So a two-sided test could either be greater than 0 or smaller than 0. So usually the way we compute this is estimate minus hypothesized value, which in this case is 0. Estimate minus 0 divided by this equals the t-value. And then we look up what probability corresponds to this. This is a rather large t-value. So we get a really small p-value. And it's highly significant, as indicated with the 3 stars. It's below 0.001, above 0, obviously, but below 0.001. Okay, but what we are interested in is beta 1 equals 1 versus beta 1 unequals 1. Well, actually, on the previous set, I said greater than 1, but we could do that. That needs some complications we don't need to worry about, meaning one-tail tests. We're sticking with the two-tail tests here, unequals. So in the procedure, we formulate the hypothesis, beta 1 equals 1 versus not. Estimate a value from the data, from the output. And then compute the discrepancy measure, beta 1 minus 1, the hypothesized value, divided by the standard error from the output, equals 2.91. Not as large as the value corresponding to the other null hypothesis, where we had 6.8. Now we have 2.9, but still, larger than 1.96, which would correspond to the normal distribution. Now this is a t-distribution, so it's the critical value is not 1.96, it's a little larger. Okay, that leads me to a question. The fourth step is to calculate the p-value or critical value. We have 30 observations. We assume a significance level of 5%. And from a t-table, there are these tables that one can print out. The critical value is 2.048. But what is the degree of freedom that corresponds to that? You see 5 possible answers. And I will leave you to answer this question and move on. So because the observed value, 2.91, exceeds the critical value of 2.048, the hypothesis is rejected at this significance level of alpha equals 5%. And so we conclude that the IBM returns are indeed more volatile than the S&P 500 stock return in general. Alternatively, we could have, rather than looking it up in a table, you can compute it on a computer directly. There are functions for that in Stata or R. Here's Stata, D means display, T-tail, and we get this probability. The important thing here is to multiply by 2 because it's a two-tailed test. So really large values for beta are evidence against the hypothesis of beta equals 1. But really small values, meaning negative values, are also evidence against that hypothesis. And because we have these two areas on the left and on the right of the probability distribution, we have to multiply by 2. And the function here, the one in theta or also the one in R, only gives you one of those areas. So we have to multiply by 2. The p-value that comes out here is 0.007, still pretty large and small, and we reject the hypothesis. Confidence intervals and hypothesis tests. We could have also used the confidence interval to answer the same question. So we use the estimate plus minus critical value times standard error. And we could look up the probability table based from a table. And we look up the value for p equals 2.5% for the same reason, because it's a two-tailed test and we're looking up the value of one of the two regions. So since combined they are 5%, one of the two regions is 2.5%. And that would give the same answer. We get here, here's the confidence interval, it gives you the same answer. Why? Because confidence intervals and hypothesis tests are two sides of the same coin. The two approaches are exactly equivalent. If it's significant, the test statistic is significant, the hypothesized value is outside of the confidence interval. If it's not significant, the hypothesis value is inside of the confidence interval. So if the p-value is 5%, then the corresponding confidence interval is 95%. If the p-value is 1%, then the confidence interval is 99% confidence interval, and so forth. This concludes this section.